Hi, my dear students. How are you? This is my third lecture. In this lecture, we will learn set theoretic algebra. You are well acquainted with algebra in your previous school days. That algebra was based on addition, subtraction, multiplication, division, etc. In set theoretic algebra, three new interesting operands are introduced. They are union, intersection, and difference. In our previous lecture, we have learned about this. In this lecture, we will learn some set identities, and later on, we use these identities as our ready-made formula. Subscribe my channel. There is no subscription charges. Press the bell icon to get notifications first whenever I upload a new video. Share this video to your near and dear ones. Okay, my dear students, are you ready to take the lesson? That's fine. Now, what do you mean by algebra? Can you tell me? Yeah, algebra is a system governed by some rules. These rules are set by mathematical properties. Some of these properties are commutativity, associativity, existence of identity, and existence of inverses, distributivity, etc. Union is commutative. What do you mean by commutativity? You know this very well. It may be you have not heard this name till now, but you have done this when you were about 8 years old. See this addition. Have not you played with these additions in your early age? In each case, you see that the result is same. In this case, we say the operation addition is commutative on real numbers. In secondary level, there was only real numbers. Beyond of this real number, mathematicians have found more numbers with similar behaviors. So, what commutativity of union on sets actually means? It means A union B is equals to B union A. It occurs like A plus B is equals to B plus A for real numbers, is not it? Now the question is how it happens in set 2 for another operator. First, we understand it by an example. Consider two sets A and B consisting of the elements alpha, beta, gamma, delta and gamma, delta, theta, zeta. Recall the definition. What A union B means? It means the non-common elements of A and B, common elements of A and B. Therefore, for these two sets, the non-common elements are alpha, beta, theta, zeta and common elements are gamma and delta. These are the non-common elements and these are the common elements. Therefore, A union B is equals to the set consisting of the elements alpha, beta, gamma, delta, theta, zeta. Thus, you have seen that in the definition of A union B, the order is not important. Thus, conceptually we get A union B is equals to B union A, but how can you prove it mathematically? Well, recall the definition. This is the definition. Then we can conclude that if an element X is in A union B, then X is either in A or in B. See this mathematical proof. Here we have just changed the order of A and B. Thus we have proved that A union B is a subset or equals to B union A. Students, would you understand why this happens? We have proved it from this statement, but why? Consider two sets A and B. Here the set A is the subset of B. Thus, this diagram very well said that if X is in A, then also the element X is in B. Thus, we have proved A union B is a subset or equals to B union A. But the proof of the identity that we have started to prove not completed yet. Now we prove the converse of this statement, that is, B union A is a subset or equals to A union B. Thus, to prove the second part of this statement, we move backwards in our previous proof. Thus, the second part of this proof is obviously done in this way, which obviously implies B union A is a subset or equals to A union B. Both the relations A union B is a subset or equals to B union A and B union A is a subset or equals to A union B together imply A union B is equals to B union A. Other set identities are these. Note that the set has no inverses under union. If you have no idea of inverse property, identity property, etc., then follow my channel by subscribing in lower right portion of your video screen. I will upload a series of videos in a regular basis. For other type of hesitation, you can comment me. For improvement of videos, your valuable suggestions are always welcome. Similar properties on intersection are these. But notice the second property. Can you call this property be an inverse property? It looks like an inverse property, is not it? We have found a set phi for the set A so that it turns to the element phi under intersection. No, students. Fallacy lies in the identity element. How? See our previous known fact. Here, -2 is the inverse of 2 because it turns the element 2 to 0. Now think about the 0. What is 0? 0 is here the identity element. Is not it? We know every real number when added to 0, the result obtained is the number itself. That's why -2 is the inverse of 2. So keep in mind, inverse exists when identity exists. So the set has no inverse under intersection. Another set identities are these. These are the distributive properties. Replacing union as plus and intersection as multiplication sign, we can get similar identities. Can you tell me which one is valid in real algebra? Right, the second one. The first one is not valid in real algebra, but it is valid in Boolean algebra. Now note these two identities. These are De Morgan's laws. Notice that the operators have changed after applying the complement. See this Venn diagram. We see that A union B can also be written in this form. Notice that A intersection B complement is equals to A minus B, and also B intersection A complement is equals to B minus A. Thus, in this lecture, we have learned several set properties such as commutativity, associativity, identity existence, inverse existence, distributivity, and also De Morgan's laws, comparison with algebra of real numbers, etc. Hi students, please do these sums, scan your answer copy and send it to me at this email address. Please subscribe my channel and also press the bell icon so that you can get notification whenever I upload a new lecture. For more clarification, you can comment me. Thank you.